We will do first one problem where the ball starts and finishes on the ground. And then we'll do, or I should say, I said ball, I should say projectile. And then we'll do a projectile problem where is kicked off a cliff or something. And so the beginning height and the ending height are not going to be the same. And then we can kind of compare those. So let's do a problem of, say, kicking a playground ball. So let's say that you're playing kickball, and here you've got the ground, and the ball gets served to you. So here's the person. And the person kicks the ball at some initial V and angle theta. So they kick the ball goes up, the ball comes down. And we want to know, let's say, where does the ball land? And what is the speed of landing? Say this is V final. So, given initial speed, initial angle, we need to find the final position. We'll say X final. The final velocity, V final. The final angle, say theta final. This here is theta initial. And then I guess we should also, do we have T? Let's see if we need to be given T. We shouldn't need to be given T. So let's find time of flight, T. All right, so just conceptually, how is the ending velocity going to be faster, slower, or equal to the initial velocity? Yes, the final velocity is going to be equal to the initial velocity because this is a perfect parabola and there is no wind resistance. So if we had wind resistance, that wind would be slowing the ball down. Because this is projectile motion, there will be no change of velocity from the initial to the final, but the velocity will change during the flight. So basically what's going to happen is it's kicked off with this initial velocity. When it gets up to the peak, up here, I'll do this in a different color. Up here at the peak, all the velocity is in the x direction. So your v here equals vx only. So this is the slowest time when it's at its apex. Then as it starts to come down again, it accelerates downwards. And so what we end up with is vf equals v initial because it accelerates just as much as it slowed down. And that also means that this theta final is going to equal theta initial. All right, so we can just go ahead and say the initial and theta initial and save ourselves some time. So a good problem on an exam would be if I ask something like that, or say if the problem asks something like that, and you know that it starts and ends at the same height, then final velocity and final angle have to be the same as initial. So that's an easy way to solve the problem without doing any math. So let's give some actual numbers though for initial velocity. We'll say that is 10 meters per second. And we'll say that initial angle equals 40 degrees. And we need to find the final position and the time. So what equations could we use to solve this? If we wanted to solve for y velocity, we could use that. But knowing what the y velocity is, then we can solve this equation for t. because if we know that the y velocity at the end is the same as the y velocity at the start, except just an equal magnitude, opposite direction, we can solve for the t that makes that happen. So let's go ahead and do that. So we will start with the Vy equation. So step one here, Vy, solve for t. Okay, so our Vy equation, Vy final, we know it's going to equal negative Vy initial. So that is going to be negative V initial sine theta. Okay, and then so that gives us this left side of the equation, the Vy for the final. And then this is going to have to equal V initial sine theta minus GT. So basically what we did is we know we have the V initial sine theta minus GT. That's fine. And then what we're plugging in for is Vy. So we knew Vy is same as it was originally, but opposite direction. And so we have just the negative V initial sine theta. So now we can go ahead and rearrange, and we have a V sine theta on one side and a negative V sine theta on the other side. We rearrange, we get negative 2 V initial sine theta equals negative G times T. We'll just get rid of the negative from each side. 2 V initial sine theta over G equals T. Okay, so we'll plug in numbers. 2 times 10 times the sine of 40 degrees, and then we divide that by 9.81. How many seconds does it take for the ball to hit the ground? Oh, and in this situation, you want to use degrees and not radians. Okay, so make sure that your calculator is in degrees. So t equals 1.31 seconds. Good. And that kind of seems reasonable for kicking a kickball. So that gives us some confidence in our answer. Okay, so then the second thing we have to solve for is final x position. So that one, okay, is going to be pretty straightforward because we actually have an equation just for x. So we'll go ahead and plug the numbers in there. So the second one, x, solve for x. So we go ahead and put in x equals x initial, we're going to say is 0. So let's say that our coordinate frame here is y, there is x. We start at 0. So 0 plus the V initial cosine theta, so that's 10 cosine of 40 degrees, times this 1.31, 10.035, or round to 10.04. So now we'll do a variation of the problem, and in this case, we will say that he's kicking it sort of off a cliff. Okay, so here we're going to say that we have this initial height, h. And let's say that h equals 3 meters. So about a 10-foot cliff. And so what's going to happen here now is this is going to extend, and it's going to land here. And we're going to have a new V final and a new theta final. Okay, so I'm going to go ahead and delete those because now we need to find the new V final and theta final. Okay, so our t is going to be different. Our x is going to be different. We can use the same equations for those probably, but actually we would need to find V final. So first, we'll have to find the V final. And then we can go and solve for t and for x using the same equations that we did before here. So we'll use the no t. And the confusing part here, or what may be confusing for a lot of people, is that this has a Vy in it. And what we're looking for is Vf. But we can use the knowledge that the x component of velocity is constant. So we already know the x component. And so then if we can find the y component, then we can find final total. So we will go over here and work that. Now, first I will erase some of this because we don't actually know the t yet. Use the no t equation. Solve for Vy. And we recall Vx equals V initial cos theta always. So we'll solve for Vy, we know Vx, and then we'll put those, using the Pythagorean theorem, we can find the magnitude. All right, so from this no t equation, we have Vy squared equals V initial squared sine squared theta minus 2g y minus y initial. So if we plug numbers in here, we'll have 10 squared times sine squared of 40 degrees minus 2 times 9.81 times final y is going to be, let's see. In this case, we have a choice of where do we want to put this coordinate frame. Do we want to put this coordinate frame at the beginning where he kicked it? Or do we want to put this coordinate frame on the ground? Now, since we already drew the coordinate frame and it's going to be hard to erase, I'm going to say we'll just leave it where he kicked it. And we'll say that initial y is 0 and final y is -3 because it went 3 down. So we'll just say -3 here. Okay, so we put this into a calculator, get Vy squared, and then we'll take the square root, and then we'll get Vy. So really, we can just say Vy equals the square root of all of that. And this is meters per second. So we got the 10.01 and the y. Now we actually have to find the Vx. So 10, so we're going to say Vx equals 10 cosine 40 degrees. We get 7.66. So, okay, so 7.66 meters per second for Vx. So now here, we will have to, we can say that this V final, so this is one side of the triangle, the hypotenuse. Then we have the Vx here, and we have the Vy here. So we can easily find V final, as well as theta final. So to get V final, we just are going to do square root of Vx squared plus Vy squared. And then for theta, we can use the tangent. So theta equals tan inverse of Vy over Vx. All right. So here we get the 12.6 meters per second, and then this is 52.5 degrees. Now, that angle, really the velocity is going negative. So we would say like this is -52 degrees. And so we can just put that negative in there. And you would get that if you did, if you use -10 for the Vy, which really, so Vy we got from the square root of this. So square root can be positive or negative. So really, because Vy is going down, this is a negative velocity. So in that case, our Vy would have it be a negative number, and we get negative 52 degrees. So on something like that basically just be thinking, is it going down or is it going up? And that gives you the sign on the angle. So we have this for theta, and we have this for final velocity. Now we'll go right back over here. And let's see. Okay, so here, Vy solve for t. We're actually going to have to go back and erase some because our Vy in this case is now no longer Vy initial. So we have Vy equals V initial sine theta minus GT. So then we rearrange, let's say we take GT to the other side. GT equals V initial sine theta minus Vy. So T equals V initial sine theta minus Vy over G. And to plug numbers into this, we have the V initial sine theta, so 10 sine of 40 degrees, and this is going up. And then minus the Vy, and this Vy is negative 10.01. So we have minus and negative, which then becomes a positive 10. And we can divide that by 9.81. All right, so T, last time we got 1.31. This should be a little bit bigger than that. Okay, so T equals 1.68 seconds, and that is greater than 1.31 seconds from the flat ground. Okay, and so just as a reality check on the situation, it should take longer to hit the ground because it has to go farther. So T equals 1.68 seconds. So now for the x equation, x equals x initial plus v initial cosine theta times t. So we'll say x equals, our x initial was just 0, plus v initial cosine theta. So really, we got that over here. V initial cosine theta is the 7.66. So we'll just put that in here, 7.66, and then times t, 1.68. So x equals 12.9 meters. And that before we got x equal 10 meters, or what was it, 10.04, and this is greater than the 10.04 from before, from the flat ground. So just as a reality check, it's bigger, that's good. But what's interesting is that with this height being 3 meters, like I guess the picture's not really drawn to scale, or we don't really know if the picture's drawn to scale or not. But it starts going a whole lot faster as it passes the 0. So VF should be greater than the initial, even the magnitude should be greater. And we said 10 meters per second here, 12.6 meters per second, and that makes sense because it should be accelerating.